Okay, so now moving forward for today anyway, and I'll try to explain a little bit why this curve is the core curve we'll be using for making statistical decisions about population parameters using sample statistics throughout the second half of the course. Why this curve is so prevalent. Because it's not only the shape of measurements like this in nature, it's not just the shape of natural variation in nature, it's the shape of purely random processes. And so as part of homework 2, I've given you an online tool for doing this, so you don't have to toss coins by hand. What I'm trying to show you here, that if you toss a coin 4 times, you expect 2 heads. Your intuition would tell you that. If it's a fair coin, you'd expect to get 2 heads. But the reality is, and this goes to the heart of the reasoning of statistics, what you expect based on certain assumptions, in this case, assuming the coin is fair, is not necessarily what you're going to get, even if your assumptions are correct. The coin is fair, you expect to get 2 heads, but if you toss a coin 4 times, you could get anywhere from 0 to 4 heads. If you were to repeat this process over and over again, I'm going to get you to do it with an online tool, but maybe I should ask you to do it more times than I'm asking you for this shape to emerge. But if you do it enough times, you toss a coin 4 times, count up the number of heads, and you say you get 2, mark off your histogram here. If you get, you got 2, then maybe you've done it again 4 times, you got another 2, stack it up, the number of times you got 4 heads, or 2 heads. You could get 0 to 4, and it turns out that if you were to do this enough times, the distribution will take on the shape of the normal curve, if you do it enough times. And so that is a core result related to what's coming up after probability this week, is called the central limit theorem. We're assuming the coin is fair and that we'd expect 2 heads, and that's our expectation, an average, and you'll see this week an expectation is an average. We could get anywhere from 0 to 4 heads, and if you repeated this process over and over again, we would see that the distribution of the number of heads from 4 coin tosses take on the normal distribution. So it's the shape of purely random processes. Thankfully it is, because we can reason around that result to make decisions about unknown population parameters. Okay, that's just giving you a taste of where we're going, and also pointing out the importance of understanding the normal distribution, at least the characteristics of it. So that's what we're doing today. The normal distribution is a foundation of statistical analysis that we reason around to make the statistical decisions about population characteristics. We need to get familiar with it for that ultimate reason, right? It's the shape, the distribution of individual measurements, as we've seen, heights, weights, diastolic blood pressures. So it's the shape of natural variation, but it's the shape of purely random processes too. So we do need to get familiar with this curve. It's a means to an end. It's laying down foundations. Not a big deal. It's characteristics. It's not just bell-shaped. 68% of values underneath the normal distribution are within 1 standard deviation of the mean. 95% are within 2, and almost all values are within 3. So, like, for example, if you went out fishing in the sea, you catch 10 fish of a particular type, you get them in the max, and get them in the standard deviation, you'll have a fair sense, at least approximately, of what's the largest fish you're ever going to catch. Because 95% of weights in a natural environment like that, of fish, would be within 2 standard deviations of the mean, even if you just took a small sample size, at least approximation. So again, there's this order. The point is, there's order to what appears as purely random variation. And that order is what we take advantage of in statistics. That's the interesting why of it, and not just the how. So what does it mean? It's bell-shaped, it's symmetric, the mean right in the middle, 50% of values below the mean. This is the height data of a mean of 174. We stripped out the histogram, forget about the blue histogram, pull that out. We approximated the shape of the distribution with the normal curve, and it's the normal distribution. Under the normal distribution, again, everybody's underneath the hood now. Everybody is underneath the hood. So 100% of people are underneath this probability distribution or normal distribution. And so what we're saying is that 68% of heights will be, at least approximately, between 166.3 and 181.7, 1 standard deviation each side of the mean. And then 95% of values are within 2. And then almost all values are within 3, but we don't really go there. We'll see how, any value that's above more than 2 standard deviations, kind of rule of thumb, considered an outlier too. So think of it that way. that's the core characteristics. In particular, this one going forward, the 95% of values are within 2 standard deviations of the mean, or between 158.6 in this case and 189.4. Okay, that's called the empirical rule for the normal distribution. It's a characteristic of this curve. Just that's the thing. We strip out the histogram. Everyone's underneath the curve. Most people are between here and here. 95% of values within 2 standard deviations. The standardized curve. Well, this data here has its own mean, has its own standard deviation, and its own measurement. What we want to start doing now is say, like, you know, if I were to select a man at random, what's the probability he'd have a height greater than 176 or less than 160? That sort of thing. What would be the probability of that? What we do is we convert to what's called a standardized z-score, from a standardized normal distribution. It has a mean of 0. It's kind of written like this: normal distribution with a mean of 0 and a standard deviation of 1. So we do the conversion like this, but the main reason is because we want to convert from the values we're working in, you know, with the mean and standard deviation we have in centimeters here, to a standard, to strip away the units of measurement, basically, by converting our, say, height value, whatever it is that we want to convert, to a z-score. And a z-score is simply our first standardized score in statistics, which means the value of z comes from what's called the standard normal distribution, which has a mean of 0 and a standard deviation of 1. Okay, so why do we do that? Because we want to ask probability questions underneath the curve. As I said, we want to ask the probability that a man has a height greater than 171, or between 168 and 172, that sort of thing. And we want to ask probability questions about our data, and really just summarize our data even more by asking these questions. And so we standardize the values to a z-score and then use a standard table or software or whatever to calculate that probability question we're asking, the answer to that question using the z-score. So this is the standard normal curve with a mean of 0, standard deviation of 1. What does that mean? It's like when you convert, think about it, look at it here. The value, whatever it is, minus the mean over the standard deviation. It serves a purpose, as I said already, to calculate a z-score, because it can be used to calculate a probability underneath this normal distribution by converting the value to the value on the standard normal distribution and then using these tables to get our answer to our question, a probability question. But it has a meaning, and it's important to understand its meaning. It tells us how many standard deviations a value is above or below the mean. Because when you look at the calculation, that's exactly what it's doing. It's the distance or the deviation of a value from the mean per standard deviation. So that's its meaning, and it's important to know its meaning as well as why we're using it as a calculation. It measures how many standard deviations a value is above or below the mean. So a z-score of 1 means a value, like a height value that we're converting to a z-score is, if its z-score is 1, it means it's 1 standard deviation above the mean. If its z-score is 2, it's 2 standard deviations above the mean, and so on. All right, so that's the characteristics of the normal curve, and it's useful. It's important to be aware of them. All right, so for this, yes, so it's simply the same thing. 68% of values have a z-score between -1 and +1, because again, it represents -1 is a value that is 1 standard deviation below the mean, and +1 standard deviation above the mean. Okay, all right. So yeah, for example, here with the height data, with a mean of 174, which we calculated, and the standard deviation, which we calculated, take a value of 184, just put it into a z-score value here, and you get 1.3. The value of 184 is 1.3 standard deviations above the mean height of 174. And that's what the z-score means. All right, break for a poll, just to make sure that you're all on the same page. Launch the poll and give you a minute to do that.